You may notice some squirrely boxes drawn on the board. Those are exactly where the lights reflect off the board. And if I write through those, it gets so washed out I can't fix it in post-production. So I'm going to write around those. Okay, we're going to do a review, chapter 14 first, and then chapter 15, and then we'll do our lab. I don't think the lab is going to take a whole 2 hours. It's all set up. We just have to do one titration, and that's it. So we should get out of here earlier than expected, as long as I don't run too long on this review. So we're going to start with chapter 14. Number 1. Oh, before I get started, are any of these problems that were in the review document, did any of those give you trouble that we need to talk about first? Okay, so we're just going to do a blanket review. Okay. Number 1, which of the following is a conjugate acid-base pair? Remember what's required for a conjugate acid-base pair. You need an acid, like with this group in here, and at least one of these. And then the pair, the base pair, would be this part of the molecule without the hydrogen. Okay? So you've got to have these match up, plus you can only miss one of these. So if we had like this, it would have to be HA minus. You can only lose one hydrogen at a time. So let's see, which one of these fits? Well, the first one is HCl and OCl minus. The part that's messed up here is this part right here. Right? They're not the same, right? So it can't be A. B, H2SO4 and SO4 2 minus. What's wrong with that picture? It's missing 2 hydrogens. You can only miss one at a time. So that one's wrong, that one's wrong. And this one, that looks like a good candidate. So the other way to write this is put the hydrogen out here. Right, and then you can see that this part matches that part, plus it's missing 1 hydrogen. So the ammonium ion is considered an acid because it can donate a proton and leave you with the conjugate base. So C is the answer to this one. Let's see, 2? Yep, 2. The hydrogen sulfate or bisulfate ion can act as either an acid or a base in water solution. Which of the following equations does HSO4 minus act as an acid? Okay, if it's an acid, then it has to release the hydrogen, it has to donate the hydrogen. Like that. So let's see, which one would that be? Oh, they've included the water. All right, so if we put water in here, then this one, we make that a hydronium, and that works. Okay. All righty. There's 2. Who's next? 3. Okay. 3. Which of the following is the equilibrium constant expression for the dissociation of weak acid, HOCl? All right, in this case, we're using the abbreviated form. We're not using hydronium, we're using hydrogen ions as if they existed separately. Of course, we know they don't. But the calculation is the same. So HOCl, right, yields H plus and OCl minus. So our K for this one would be these guys. Divided by this one. And that one looks like A. A works for that one. All right. Number 6. A solution in which pOH is 12.1. Okay. Would be described as a very acidic, slightly acidic, neutral, very basic, slightly basic. Okay. There are 2 ways we can go about this. We can say, all right, if we know that that's pOH, then pH would be 14 minus 12.1, correct? Yeah. So that would be 1.9 pH, which is very acidic. The other way to look at it is if the scale is from like this, pH, and this is acidic, and this is basic, then the pOH scale is going to be just the opposite. It's going to be 12 here, 7 there, 1 there. So if pOH is 12, it's very acidic. You can look at it that way too. Seven, which of the following indicates the most basic solution? All right. Hydrogen ion concentration of, okay, let's do these one at a time. 1 times 10 to the minus 10, is it? Yeah. So what would the pH of this one be? That's 10, right? pOH is 6.7. B. pOH equals 6.7. So the pH is equal to 7.3, right? 14 minus 6.7. Yeah. And C, oh, which is most basic? Well, okay, I've already started with pH, so we'll stay with it. If the OH concentration is 7 times 10 to the minus 5, then the pOH equals, let's take the negative log of that value. 7, 10 to the minus 5 is 4.15. So the pH would be equal to 9.85. Right? All right, and let's see, CD. pH equals 4.2. At least 2 of the solutions are equally basic. Well, let's see. There's a pH, there's a pH, there's a pH, and there's a pH. They're not the same. None of them are the same. So we can pick one out. The most basic is A. 10. Okay. Let's see. 8. Yeah. Let's look at 8. We'll put 8 over here. All right. Which of the following solutions contains the strongest acid? Strongest acid. Okay. If you want the strongest acid, you need the largest K value, right? So the largest K value is E, with a K of 7.2 times 10 to the minus 4. So that's the strongest acid. And those are all acids. I had to check myself. Yeah, they're all acid, undissociated acids with the K value. Right, so we just look for the largest K value. Okay. What would be just for argument's sake, what would be the strongest conjugate base out of that bunch? Okay, strongest acid is going to make the weakest conjugate base. So it won't be that one. It'll be one with the weakest acid to make the strongest conjugate base. Now, the tendency there is to look at just the first one. And if that's the case, then we pick A, right? But we have B with 2 K values. And the second K value is extremely weak. So that would make an extra strong conjugate base. So B would be the best answer for that one. If that were the question, which one's the strongest conjugate base? It would be B. B, by the way, is ascorbic acid, vitamin C. It has 2 dissociable hydrogens. Okay. That was 8. Let's see, number 9? Yeah, number 9. Let's see. Which of the following statements are true? Okay. The pH of a strong acid is always lower than the pH of a weak acid. Is that true? What's pH based on? It's based on the hydrogen ion concentration, right? So 2 factors go into hydrogen ion concentration. One is what's the Ka of the acid and what's its concentration. So you can have a weak acid with extremely high concentration give you a higher hydrogen ion concentration than a strong acid with a low concentration. So A is false. Right. The pH of a solution can never be negative. Is that true? No, it can be negative. Right. Let's see. What's an example of a negative pH? If we have a hydrogen ion concentration equal to, 100 mole, no, that wouldn't be right. How about, that's too extreme. Say 10 molar. So that'd be 10 to the first power. Negative log of 10 to the first power would be -1. There you go. Yeah. So we can calculate a concentration that would give us a negative pH. So B is false. You can have negative pH. It's just not very useful. How about C? Let's see. C says Ka equals 1 over Kb. Is that true? I don't think so. No. What is Ka if we know Kb? Let's see. Kw divided by Kb. Remember, Ka times Kb equals Kw. So C is false. How about D? At least 2 of the statements are true. Nope. All the statements are false. Yep, that's true. E is true. All right. 11, 12. Yeah, squeeze both of them in there. 11. For the stepwise dissociation of H3PO4, which of the following is not a conjugate acid-base pair? All right. So if we're going to go the conjugate base of this one is H2PO4 minus, right? And then the next dissociation will take this one and strip off another hydrogen and leave us with a 2 minus. And then we'll take this one, 2 minus, strip off another hydrogen and leave us with PO4 3 minus. So those are the pairs that would work. And let's see, which of the following is not a conjugate acid-base pair? HPO4 2 minus. Okay, A is right. H3PO4. Yeah, B is right. C, H2PO4 minus. 2PO4 minus and HPO4 2 minus. That's right. H2PO4 minus and PO4 3. No, D is wrong. And I don't know why E is in there, because that had nothing to do with H3PO4, except, well, I guess it could be. Hydronium ion is the acid and the H2O is the conjugate base. That's true. So we said D was right, correct? How about 12? For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? Okay, 0.1 molar diprotic, 0.1 molar doesn't matter. That's just fluff. What we're interested in is which one is produces a significant concentration of hydrogen ions that would affect the pH from the second dissociation. In order to answer that question, how close are the two Ks to each other? Okay, so the first one, 10 to the minus 2 and 10 to the minus 7. That's 5 orders of magnitude apart. No influence whatsoever from the second one. 10 to the minus 4, 10 to the minus 8 for the second one. That's 4 orders of magnitude away. No influence there either. C, 10 to the minus 4 and 10 to the minus 9. That's another 5 orders of magnitude difference. 10,000. 10,000. 100,000. No influence there. 10 to the minus 3 and 10 to the minus 4. And in fact, the 10 to the minus 4 is almost 10 to the minus 3. It's 9.3 times 10 to the minus 4. That would be a significant influence on the pH. D would be your answer. That second dissociation would produce significant amounts of hydrogen ions to influence the pH. Now, I don't know of any acid that does that, but if it were, that would be an influence on the pH. All right, how about 16? Okay, that's a standalone there. 16. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? The highest pH, which would be the most basic? A strong acid or a weak acid? We can pretty much count those out because they're going to be at acidic pHs anyway. How about a potassium salt or a weak acid? C, potassium salt of a weak acid. So what's going to happen when it goes into solution? Well, it's going to completely dissociate. And that right there was derived from a weak acid, which makes it a very strong base. All right, so now it's going to react with water and strip off a hydrogen, right? Because this is a weak acid, strong base. Strip off a hydrogen and leave you with hydroxyl. So that one, C, would be the strongest of the two. If you say potassium salt of a strong acid, it's going to stay like that. It's not going to react with water. Right? Because it's from a strong acid, it wants to be there anyway. Ammonium salt of a strong acid. Ammonium salt of a strong acid. Well, the ammonium salt, just for argument's sake, the ammonium salt that goes into solution with a strong acid, this is going to stay like that. And this, if it dissociates at all, it's going to produce hydrogen ions. So that's going to be an acidic solution, right? So the best answer is C. That weak acid, the conjugate base of the weak acid, is going to produce the basic solution. Okay. All right. Just checking. I don't see any heads spinning around, and I'm in good shape. Let's see. 19. Let's see. Does this have some? Yeah. Okay. 19 is part of this group. Select the answer that best describes an aqueous solution made from each of the following substances. Oh, okay. So we're just going to put this in solution. Solid ammonium acetate goes into solution. Solid ammonium acetate. 19. I'm going to put it down here. So if ammonium acetate goes into solution, and here we go. C2H3O2 goes into solution. It's going to completely dissolve and make that plus this. Okay. Then this, what reaction would this component do in water? Plus water. And it's going to have an equilibrium with this one, the conjugate base, plus the hydronium. Okay. And this one is a conjugate base of a weak acid. So it's going to latch onto some protons from water. So this reaction would be here, 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 like that, plus water. And this would give you acetic acid, actually, O2 plus OH minus. Okay. So this is a pKa, and this is a pKb. Okay. So does it tell us what the pKa is? Yeah. The K, well, it tells us what the Ka is. Okay, so we'll do that. What's the Ka? So the Ka for this reaction is 5.6 times 10 to the minus 10. 5.6 times 10 to the minus 10. And this one is 5.6 times 10 to the minus 10, the Kb. Does it say Kb? Yes. 5.6 times 10 to the minus 10. All right. Nobody wins. It's a tie game, right? This one is the same magnitude as that one. This one's going in one direction. This is going the opposite direction. They cancel each other out. This is a neutral solution. If this one had been a bigger number than that one, then it would have been basic. If this one had been a larger number than that one, it would have been acidic. Okay? We can't use the rule of thumb with these because they're too weak reactions. So we got to compare the actual numbers. And as it turns out, they're exactly equal. So we got a neutral solution.
So you said which number was bigger of the acid?
Oh, if this number were larger than that number, it would be acidic. If this number were larger than that one, it would be basic. Which one is a greater equilibrium to the right? So if this is a larger number, it means it's over here, but more so than this one is. All right. Oh, we get another one. Let's see. Can I save myself some writing here? 20. Ammonium perchlorate. Okay, so I'm going to change this. Perchlorate, ClO4. And this would be ClO4 minus. This one would be ClO4 minus. And this would be HClO4. That's the same. Should be Ka is the same here. 10 minus 10, yeah. And ClO4 minus is about 10 to the minus 21. Okay. So this anion is the conjugate base of a very strong acid. So that's why it's a very weak base. That's what that means. Extremely weak. So this value here favoring this reaction is greater than this one. So this one, the acidic, would win. It would be an acidic solution. All righty. 22. Which factor listed below is most important in determining the strength of an oxyacid? An oxyacid. What's an oxyacid? Something like that. It's got an oxygen in it, at least one. It could have more than one. Okay. So which factor is most important? The number of those. The more oxygens you have, the more acidic the molecule. So a number of oxygen atoms present in the molecule, that's the key. And the reason for it is, if you just have one oxygen, oxygen is an electronegative atom, right? It's one of those that's responsible for hydrogen bonding. If you only have one, it has an electron withdrawal effect of a certain level. But if you add another one, right, you boosted the electron withdrawal and makes this bond weaker. So that's a stronger acid. And then if you put another one in there, it makes it even weaker. And I think perchlorate has another one. It has 4. So that's why it's an extremely strong acid. Perchloric acid is very strong. It weakens that bond so much that the hydrogen just wants to jump off the molecule. And that makes for a stronger acid. So the number of oxygens is the determining factor in the strength of the acid. (24) Which of the species below, when dissolved in water, will not produce a basic solution? All right. Will not produce a basic solution. Okay. Process of elimination. Barium hydroxide. That's definitely basic. Right. Barium oxide. What does barium oxide do when it dissolves? Excuse me. When it reacts with water? Well, it produces barium hydroxide. Yeah, barium oxide produces barium hydroxide. How about B? Ammonium. What does ammonium do when we dissolve it in water? Well, it reacts with water and makes the ammonium ion plus hydroxyls. That's basic. So process of elimination, well, it says none of these, so we got to do SO2. So what does SO2 do when it reacts with water? Well, it produces H2SO3, which is acid, right? It's one of those acid anhydrides. When you have an oxide formed from a nonmetal, a nonmetal and oxygen dissolved in water always makes an acidic solution. Whereas a metal oxide always makes a basic solution. All right. Let's see. How we doing? 24, 25, and 26. Which of the following species cannot act as a Lewis base? Okay. Let's look at it this way. In order to define a Lewis base, what would be a Bronsted base? It's one that can accept a proton. So if a proton is accepted, what do we have to do to form a bond? We have to supply the electrons, right? So a Bronsted base would accept a proton, but it would have to supply the electrons. So a Lewis base donates electrons, and a Lewis acid accepts electrons. So a Lewis base would donate electrons. Okay, so which ones look like they can donate electrons? Well, let's see, definitely O2, O2 minus. It's got electrons to donate. OH minus, yeah, it's got electrons to donate. CH4, be kind of hard for that one to donate, wouldn't it? Because it's got a complete octet, no free electrons at all. So that's a good candidate. How about D? H2S. Okay. If you draw the Lewis structure for hydrogen sulfide, it's got those two lone pairs. It can donate those, right? There are no lone pairs here. And E, ammonia. Well, ammonium looks like this. Right? It's got the trigonal base, and it's got those lone pairs. So that would be a base also. Base, 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 not. So methane would be a very poor candidate for a Lewis base. '26, I think. Yeah. Which of the following cannot be a Lewis base? Oh, we got another one. All right. So how about N3 minus? Oh yeah, it's got lots of electrons. NH2 minus, yep, NH2 minus, and NH2 minus, NH3, NH4 plus. So that would be like this, that. And all of that tetrahedral structure would have a plus charge. It's not going to donate electrons. '26. What's next? 27. Which of the following species cannot act as a Lewis acid? So these cannot accept electrons. All right. All those positively charged ions, they can accept electrons from here to Sunday. But that H minus would act as a Lewis base, but not a Lewis acid. It cannot accept more electrons. For one thing, what's its electronic structure? Right? It's got a complete s orbital. There's no place to put them easily. I didn't even write the number up for that one. 27. How about 30? All right. Given the following values of pKa, determine which is the weakest base of the answers listed. All right, those are all pKa's. Those are all acids. So the weakest base is going to be from the strongest acid. The strongest acid is HClO2 out of that group, 1.95 pK. So HClO2 is going to produce H plus and ClO2 minus. ClO2 minus, yeah. Wait a minute. Okay, this is a trick question. You're given pKs for everything except for the one that produces that last one. Cl minus. Where did it come from? It came from a strong acid. Yeah, I almost fooled myself. Cl minus is the weakest base of that bunch because it comes from a strong acid. It doesn't even have a pKa because it's so small. It'd probably be negative. Right, so that was a trick question. That's why I put that one in there. The temptation would be to go to this one, ClO2, until you look down there and say, uh-oh, Cl minus comes from hydrochloric acid. Let's see. Come on. There we go. Skip any? No. 38. 38. Okay. Carbonic acid is a diprotic acid, H2CO3. Yep. H2CO3. And it will dissociate first time would be this, HCO3 minus. Second time, HCO3 minus plus CO3 2 minus. Okay. The Ka for the first dissociation is 4.2 times 10 to the minus 7. Ka1. Ka2 should be a smaller number, 4.8 times 10 to the minus 11. Okay, at 25 degrees. The ion product for water is, all right, we should already have that memorized anyway, 10 to the minus 14. For water, what is the OH minus concentration of a solution that is 0.18 molar in sodium carbonate? Okay. Which one of these reactions is going to control? Well, both of these reactions are more probable because they have a larger K value than this one. So the dissociation of water will have no influence at all. But the one that controls, since these are 4 orders of magnitude apart, this is the controlling reaction right here. So we have H2CO3 produces H plus plus HCO3 minus, and we're starting off with 0.18 molar in sodium carbonate. sodium carbonate, 0.18 molar, correct? 0.18 molar. All right, so when it goes into solution, it's going to produce same concentration of carbonates. Sodium is not going to do anything. Major species here, CO3, 2 minus, and water. Okay, so what we've got here is a Ka for this reaction, but the reaction that we're going to see is this one. Which will produce HCO3 minus plus OH minus, and the Kb is going to be 1 times 10 to the minus 14 divided by 4.8 times 10 to the minus 11. So let's see what the Kb is for that reaction. Oh, I need to change my display. Why does it keep going back to that? Display, here it is. Display. Display scientific, here we go. Let me do that again. 1 exponent 14 and 4.8 exponent minus 11. Okay. 2.083 times 10 to the minus 4. Okay. All right. So we're going to have this much in solution, 0.18 molar of this one. Okay. So let me see if I'm on the right track so I won't waste your time. I think I know where I'm going, but yeah. All right, so we got that. So this is our ice table right here. We've got none of this, none of that. So we're going to lose some of this because this is a very strong base. Minus X, this is going to be X, and this is going to be X. So we're going to have an X here and an X here, and 0.18 minus X there. So this reaction references this value here, Kb. And the Kb is equal to HCO3 minus plus OH, excuse me, times OH minus over CO3, 2 minus. There we go. Okay. So this one is going to be X and X, right? And this is going to be 0.18 minus X is equal to 2.083 times 10 to the minus 4. All right, in order to avoid a quadratic, we're going to say this one is essentially 0.18. And we're probably pretty safe because this is 0.1 minus 4. If it were minus 3 or minus 2, that might be iffy. All right, so in the interest of time, X should be 6.12 times 10 to the minus 3, which is the hydroxyl ion concentration. 6.12 times 10 minus 3, that's A. Now, my question would be, once you've got HCO3 minus, which is a fairly strong base of its own, HCO3 minus here, what would be the KB here? Would it be a competitor for that one? We'll do a quick calculation. 1 exponent 14 divided by 4.2 exponent 7 minus. There we go. 0.2 exponent 7. This will be 2.38 KB for, well, I didn't write it out, but if we were to take this one, the KB would be 2.38 times 10 to the minus 8. Okay. So here's the reasoning I'm trying to get at. If we were to take this one and do a similar reaction like this, react it with water and get hydroxyls, would it produce a significant amount of hydroxyls that would influence this overall? Okay. So if you look at the KB for this one, 10 to the minus 4, this one is 10 to the minus 8, right? 4 orders of magnitude weaker. So the same logic we're using for this one is the logic we used for acids, right? If they're very far apart, then the second dissociation has little influence on the pH. Well, if we work backwards and go with KBs, then this reaction is 4 orders of magnitude stronger than that one. So this one's not going to influence the pH at all or influence the hydroxyl ion concentration. Does that make sense? It's a similar reasoning, right? This is the dominant reaction, 10 to the minus 4 KB. This was 10 to the minus 8 KB. If we were to do the same reaction here with, take that one and react it with water, would it produce enough hydroxyls? No, it wouldn't. Wouldn't produce enough hydroxyls to influence this value. That's why we can stop here. Okay. All right, that one took a while. 38. Okay. 39. Calculate the pH. This one doesn't have a 39 on it. Huh. Did I just not print that page? Let me see if there are any more. 39. No. Okay. So I just missed that one. Let's see if we can make sense of it. Maybe that's why I put it in here, because I didn't have it on there. Calculate the pH at equivalence for the following titration. 0.1 molar HOCl. So this is what we're given. 0.1 molar HOCl. Hypochlorous acid. With a Ka of 3.5 times 10 to the minus 8. Okay. And 0.1 molar sodium hydroxide. 0.1 molar sodium hydroxide. So we're going to do a titration with this acid and that base. All right. at equivalence, okay? So since they're the same concentration, we're going to have exactly the same volume of both when we reach equivalence. And the titration will look something like, let's see, here's base, here's pH. pH of this is going to be it's going to be acidic, but not as acidic as acetic acid. It's going to be up in the range of 6, maybe. So it'd be like that, then it'll go like that, okay. And this is, we want to know that pH right there. Okay. So here's what I want to do. I want to subdivide this into 2 problems. One is the stoichiometry problem. Stoichiometry problem says we're going to react all of this with all of that and produce OCl. So what's the concentration of OCl going to be? OCl minus. It's going to be 0.1 molar. Right? Because if we take this one, HOCl and plus sodium hydroxide, that's going to yield sodium hypochlorite and water, right? Acid base, salt, water. This concentration is 0.1 molar. What's this concentration? 0.1 molar after the reaction. So that means this concentration right here is 0.1 molar. So the stoichiometry says we're going to end up with this ion at 0.1 molar concentration in solution. Okay, so now we go to the equilibrium reaction. All right, so that was the stoichiometry. Now the equilibrium says OCl minus plus water. It's like we go one way and then we're going to work our way back. Gives us HOCl plus OH minus. Here we go. So now we can do the ice table from this one. Right, we start off with 0.1 molar and essentially nothing over here. And then we're going to lose some of this. We're going to add some of this. Right. So we're going to have an X here, an X there. This is going to be 0.1 molar minus X. Okay. So we need a KB for that one. There's the Ka. So the KB is going to be 10 to the minus 14 divided by 3.5 times 10 to the minus 8. Exponent 14 and 3.5 times 10 to the minus 8 exponent 8 divided 2.857 times 10 to the minus 7. 2.857 times 10 to the minus 7. Just checking myself. 857. Yeah, okay. So this is going to be X times X, or X squared, divided by 0.1 molar. Now notice I dropped that X off of there. I did 2 steps at once. Actually, I did 3 steps. X times X and 0.1 minus X, where X is so small it doesn't matter. So if we multiply this one times that one, we'll skip another step. So what we're looking at is the square root of 2.857 times 10 to the minus 8. Because I multiplied this one times 0.1. Okay. So let's see. And square root. There we go. 1.69 times 10 to the minus 4. 1.69 times 10 to the minus 4 molar. Oh, it asks us for pH. Okay. What is X? X is OH. So this is OH minus. So POH now is the negative log of that number. 3.77. So pH is equal to 14 minus that. 10.2. Close enough, 10.1. Okay, rounding error. Did that make sense? This is one of those where we have a two-step stoichiometry first. And you can think that for any titration, you're going to do stoichiometry first. And then that will give you the values for working on the reverse reaction to go backwards toward equilibrium. I should have put that one in the document. I don't know why I missed that. Let me make myself a note. 39. Need worked problem. Fact. Yeah, that's enough. Let me take a quick. Here it is. So I don't have to dig through the video to find it. I'm going to take a picture of this one and try to get it into the work problems document. That'll do it. Right there. Yep. Okay. I don't know why I missed that. Probably in a hurry. That's it for chapter 14. Now we can move on to 15. And talk about buffers. All right. Good on time. Got an hour. So let's stop this share. There we go. And share 15. Here we go. Come on. There it is. Okay. Let's bump it up a little bit. All right. We'll start this one on number 4. Try to erase the board. I said what? Yeah. Okay, a weak acid, HF, is in solution with dissolved sodium fluoride. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? All right, so we've got a situation here where we've got HF supplied at one concentration and fluoride supplied at the other concentration. Right. We supply hydrofluoric acid and fluoride from sodium fluoride. Right. Those are in solution together. We have some of this and some of that. That's the scenario. Now, that's our buffer. If we add HCl, what are we adding? We're adding hydrogen ions and chloride ions, right? Chloride ion is going to react with anything? No, only the hydrogen. So what does the hydrogen react with? We'll look at it this way. You're supplying Le Chatelier, supplying hydrogen ions, it's got to react with fluoride. You're supplying the product side. So it reacts with the fluoride ion, which is C. Okay? We'll start off simple. And 5. Which of the following is true for a buffered solution? All right. A, the solution resists change in its hydrogen ion concentration. Is that true? Yeah, it does. It resists the change in hydrogen ion concentrations, which translated pH. Okay, the solution will not change its pH very much, even if a concentrated acid is added. That's also true. That's characteristic of a buffer. C, the solution will not change its pH very much, even if a strong base is added. That's also true. Any hydrogen ions will react with the conjugate base of a weak acid already in solution. Yeah, we just proved that one. Right. So if the weak acid is this, and this is the conjugate base, that's what the hydrogen ions interact with. That's what they attach. So all of them are true. All those statements are true. All right. 5, 6, 7, 8. 8 and 9. Can I get both of them? Yep. 8. How do the pHs of buffered solutions compare? The pH of buffered solution 1 is greater than that of buffered solution. Wait a minute. Is it referencing something? Yeah, something above. Okay, let's try this again. You have 2 buffered solutions. Solution 1 contains 5 molar acetic acid and 5 molar sodium acetate. So 1 has 5 molar each. 5 molar, that's my abbreviation for acetic acid, and 5 molar there. Solution 2 has what? Solution 2 has 0.5 of each one. 0.5. 0.5. Okay. The pH of buffer solution 1 is greater than the pH of 2. What determines the pH? Think Henderson-Hasselbalch. The pH of a solution depends on the pKa of the weak acid plus the log of the ratio of the conjugate base to the weak acid. So this ratio is what determines the pH. Okay. So these ratios are exactly the same, 1 to 1, 1 to 1. Their pHs should be exactly the same. C. Okay, they're not the same solutions. Their pHs are the same, but they're not the same solutions. How are they different? This one has a much higher buffer capacity. It will absorb more hydrogen ions or more added hydroxyls than this one will. But still, they're starting at the same pH. In fact, they should be right in the smack dab middle of the buffer range. All right. How about 9? Which of the following is the net ionic equation for a reaction that occurs during the titration of nitric acid and potassium hydroxide? This is kind of a trick question. The net ionic equation of an acid-base titration is always, say 9. Hydrogen ions plus hydroxyls yield water. That's the net ionic equation of an acid-base reaction. E. Strictly speaking, that should be hydronium. But it works. Okay, in a titration of a weak acid HA with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. Okay, so the stoic point is pH 10. All right. Which of the following indicator acids would be best to use to mark the endpoint of this titration? So what are we looking at? If we know that the endpoint, the stoichiometric point is pH 10, then the endpoint should be approximately equal to the pKa of the weak acid indicator. All right, so if we're just given powers of 10, the closest one to that is 10 to the minus 11, which would be a pH of 11. Right, so B would be your best choice. And typically speaking, you want the pH, if you're doing a base sodium hydroxide titration with a weak acid, your best place to have the pKa for your indicator is greater than the stoichiometric point. There's less likelihood of error if the pKa is greater than this value. So 11, yeah, equals 11, that would be a good choice. And the range is what? Plus or minus 1. So it'd be 9 to 11. 9 to 11 would be the pK range that we would want. And there's nothing close to 9, so that's a no-brainer. 11 is the only one that works. Right. Okay. Now, do you remember why plus or minus 1 is the choice for pH range? Human perception. It's got to be 10 times one way or 10 times the other way to see a color change. So that's why we have pH plus or minus 1. So we snuck a little physiology in there on you. 13. All right, let's see. Which of the following solutions would be described as a buffer solution? Okay. In order to have a buffer solution, you need two things. You need either a weak acid or a weak base. Usually a weak acid, but you can still make a buffer with a weak base because a weak base will make a strong acid conjugate. And you need the conjugate base or the conjugate acid. All right, so let's see if we've got any of those in there. Let's see. The first one, acetic acid, CH3COH. Did I ever show you that one? Acetic acid in your textbook is written this way, right? Okay. Another way to write it is CH3COOH. Here's the acidic proton there. Here's the acidic proton there. This just gives you structural information, right? This methyl group is going to look like that, that, right there. Then we're going to have a carbon. Then we're going to have a carbonyl group, and then we have the acidic group. There's your proton. Okay, that's why it's written that way. Just in case you ever see it again. I haven't been using that because your book doesn't do it that way. Okay, let's go back. Would the first one be a buffer solution? A. No, it's got an acid and an acid. It can't be. There's no way. Hydrochloric and acetic acid? No. How about acetic acid and sodium hydroxide? That might be, right? You got a weak acid and you added a base to it. And what does the base do? The base takes, I'll write it the way they wrote it. It takes the hydroxyls from the sodium hydroxide, right? And it gives you water plus CH3COO minus. There's your conjugate base. Now this isn't, let's see. This isn't the best, but it is a buffer solution, right? It still leaves you some of this and produces some of that. In fact, it only leaves you 0.05 molar of this, and it produces 0.2 molar of that after the titration. So it's not an ideal buffer, but it is a buffer because it produces both the acid and the conjugate base. Let's see, C would be sodium bromide and hydrobromic acid. All right, that would be okay, except HBr is a strong acid. It will not work. It has to be a weak acid or a weak base. Like NH3 is a weak base, right? But we're titrating it with a base. That's not going to produce ammonium. If you want a buffer solution with this one, you've got to have that one, right? You can't add base to it and make a buffer. You have to add acid to that one. And then the last one is a strong acid, strong base. No way. You can't make a buffer out of those. All right. So our best answer is B. Okay. That's 13. 14? Yep, 14. All right. See, it looks like we're in the same ballpark. Which of the following mixtures would be classified as a buffer solution? All right, so let's go down. A, hydrochloric acid and potassium chloride. Can't make a buffer out of a strong acid. That's just it. A's false. How about B? Okay, there's a weak acid, yep. 50 milliliters of weak acid, 55 milliliters of 0.1 molar sodium hydroxide. What have you done there? You have completely neutralized your acid, right? There's no acid left. There's lots of weak base, strong base, conjugate base in there, but there's no acid left. So you can't do that. So B is false. It met one of the conditions, but not the second one. Let's see, 50 milliliters of 0.1 molar acetic acid and 25 milliliters of sodium hydroxide. Perfect. They're the same concentration, but only half the volume of sodium hydroxide, which will use up half of the acid to make 0.05 molar acetate ion and leave behind 0.05 molar acetic acid. That's 1-to-1 ratio. That's a perfect buffer right there. C. I don't think we need to go any further. We found our buffer, our ideal buffer, in fact. All right. How are we doing on time? Okay, we're okay. 19. Let's see if I can get it all in there. Consider the following indicators and their pH ranges. Okay. In this case, we don't have to estimate plus or minus 1. They're actually giving us the pH ranges where you see a color change. So assume an indicator works best when the equivalence point of the titration comes in the middle of the indicator range. Okay. For which of the following titrations would methyl red be the best indicator? Methyl red has a 4.8 to 6.0. 6.0 pH. Methyl red. Okay. So what we want is what's the middle of this range? 14.8 divided by 2 is 7.4. So 7.4 would be the middle of that range. Have we got one where we're expecting the end point, the stoichiometric point for the reaction, to be near 7.4? Well, let's see. It was the equivalence point of the titration comes in the middle of the indicator range. Okay, for which the following titration. Okay. Nitric acid and potassium hydroxide should have an equivalence point at exactly 7. Aniline would be 10 to the minus 10 kb for aniline would be very high pH, right? So it'd be well out of this range. That's B. C, 1.8 times 10 to the minus 5. So what would the negative log of that value be? 1.8 times 10 to the minus 5. 5 log, change sign. That's there we go. Take the log, and then that's 4.7 kb or 7 pkb. Oh, that's the buffer range. We want to know where's the equivalence, the stoichiometric point. All right. So NH3 and 0.1 molar HCl. All right. So we're going to end up with NH3 after it's titrated with hydrochloric acid. Okay. No, we're going to end up, NH4 plus. And that's going to give us NH3 plus hydronium. So what we need is not the pKb, but the pKa, because this is a pKa or Ka. So 1.8 times 10 to the minus 5 divided into 1 times 10 to the minus 14 is the Ka for this reaction. .6 times 10 to the minus 10. 10 to the minus 10. Okay, and that's going to be ammonium ions, hydrogen ions over ammoniums. Okay. So if we went all the way, this is a stoichiometry problem first. If we went all the way to the right, we would have 0.1 molar, 0.1 molar here. So 0.1 there, and this is X and this is X. So we got 5.6 times 10 to the minus 11 1.1 times that one, and then square root for the x. Exponent minus 11. Take the square root of that. 7.48 times 10 to the minus 6. 7.48 times 10 to the minus 6 equals hydrogen ion concentrations. Okay. So the pH then would be the negative log of that. I did something wrong. Let me do it again. 7.48 exponent minus 6. Enter. Take the negative log. Okay, 5.1. pH 5.1. Oh, that's not right. Why didn't you tell me that? That should be 12. Half of that would be 6.4. Just let me jabber on. Okay. That's not even right there. There we go, 5.4. Well, this one is 5.1 is the endpoint, so it's going to be right in here. Right, that takes some time to work out. And the A couldn't possibly be it because strong acid, strong base are going to have an endpoint at 7. Aniline, we already threw that one out because its endpoint is going to be very high. It's not going to be acidic. And we did ammonia calculation already. How about HF? HF and sodium hydroxide are going to produce a basic. It's kind of like, think of it, I use as my reference point acetic acid. Right? Acetic acid is going to have an endpoint or a stoichiometric point during titration in the neighborhood of 9, between 8 and 9. So, and it's 10 to the minus 5th. So if HF is 10 to the minus 4th, it'll be maybe a little, actually be higher. No, it'd be lower. So it'd be lower than 9. It'd be like in the neighborhood of 8 would be its stoichiometric point. Well, I mean, we can figure it out, but we already did this one and it's right on the money. That looks like an extra credit problem there. It takes so long to work out. But like before, any of these titrations, think of them in terms of stoichiometry first, then equilibrium. 23. $50 milliliter solution of 0.035 molar hydrocyanic acid is titrated with 0.033 molar solution of sodium hydroxide. What's the pH of the acid solution after 15 milliliters of titrant has been added? Okay, so let's do the stoichiometry first. Stoichiometry is going to be hydrocyanic acid plus sodium hydroxide. And that's going to give us water, of course, right? Plus sodium cyanide. Okay. So we got 50 milliliters of 0.0350 molar. 50 milliliters of 0.035. No. Yeah, 50 molar that, and sodium hydroxide, we have 0.0333 molar. 0.0333 molar. And it said that we added 15 milliliters. Okay. All right. So what's the stoichiometry here? Well, we're not going to use all of this up. We're only going to use part of it up. So how many moles of hydroxyl are we going to produce here? 15 times 0.033. Actually, that's 0.4995 millimoles. Of sodium hydroxide, and 50 times 0.0350 is 1.750 millimoles of hydrocyanic acid. Okay, we're going to use all of this up, right? So there's nothing left in this one, and they're 1-to-1, right? 1-to-1 reaction. So what's left of the HCN? 0.4995 millimoles. So let's see, if I got that in here, I can subtract them. Yeah, just flip that, subtract. 1.251 millimoles of HCN will remain after the stoichiometry. How much of this was produced? And we're looking at that item right there. How much of that was produced? Well, it's the same as this one, right? Exactly the same. 0.4995 millimoles of cyanide ion. Okay, now what we're looking at is the equilibrium part. Let's see. Okay, this one will be worth doing. And it shouldn't take too long either. See, I need a marker. Let's try blue. 25. All right, a certain indicator, HIN, has a pKa of 9. So the indicator is this, and it's going to dissociate into these. Oops, sorry. And the Ka is equal to 9. Okay, color change becomes visible when 7% of it is IN minus. At what pH is this color change visible? So this is at 7%. So what's this one left over? This one's 93%, right? Okay, so the ratio pKa equals, plus log of IN minus over HIN. That would be Ka, pKa. That's good. Is 9 plus the log of the ratio of these two. Now we have a ratio of 0.07. So a log of 0.07 is that, and then add that to 9 is 7.8. 7.8 rounded up, 7.85. So the pH is 7.85. That's where we're going to see the color change. All right. That was quick. Is that it? Yeah. Should be it. Oh, no, we got 2 more. Okay, these are important. In the figure below, the pH at first hydrogen equivalence is approximately what? Okay. First hydrogen equivalence. So we started at a low pH here, and we're adding base. So the first hydrogen equivalent is when we've used up the hydrogen, the first hydrogen of the acid.
I have either of these.
You don't have them? Well, shoot. And they're not in the document, I don't think.
I'm looking at the review document right now, it's in the 25.
Huh. Okay. Mine goes on over to 27. All right, so let's maybe should I sketch the graph? There's the graph. All right. So this is added base, probably sodium hydroxide. This is pH. We're starting off at pH 1. So this is 2, 4, 6, 8, 10. Starting off here. And it goes, climbs up. Let's see. 2, 3. That should be enough. So this is 1, 2, 3 moles of base. Okay. So at a half a mole, we're up to about 2.5. At half a mole, we're up to about 2.5 right here. And then that's in the middle of the range. And our equivalence, first equivalence is at pH 6. And 1 mole right here. So we're going to go up like that. And then we're going to get up to about 8.5 right here before it starts to level off again. And that's just to the right here. And then it's going to flatten out. And it's going to reach the middle of that one at 1.5. Right here. Okay, and then it's going to go out here like that. And it's going to reach its second equivalence at about pH 12 and 2 moles. So I need to squinch it a little bit. About right here. Okay. So the first question is, at what pH is the first equivalence? So the first equivalence occurs in the middle here, right? pH 6, right there. That's the first equivalence, pH 6, or 6.02. Okay. Where would this acid best be used as a buffer? So what you need there is this part here. This should be a little flatter and flatter here. So it'd be either here around 9 or here around 2.5. Uh, 10 is closer. That's not right there. I drew it wrong. Right. 10 should be right in here.
What was 26?
26 is 6. The first equivalence is right here. Right. This is the first buffer range. This is the first equivalence. Right. Have either one of y'all had calculus?
Not since high school.
Okay. If you remember the inflection point, curve up versus curve down, where they change directions, that's what we're looking at right there. That's the inflection point. And that's the equivalence point for a titration. This is the first hydrogen titration right here at this pH, pH 6. And then the best buffer range is right in here first buffer range would be in the neighborhood of 2.5, but that's not a choice. The next buffer range would be 10, in the range of 10, which would be, excuse me, wrong direction here. Right. So there's no 2.5 selection there. So you have to go to the next buffer range, which is 10. And the 10 is in the flattened part of the curve. That's the buffer range. That's why I put that one in there for reading the graph. Okay.